Thank you, that's perfect. That data point represents the center of our sample. Now our sample has a margin of error too, but that's the center of our sample. And that center is the most likely location for the center of the overriding population of secondhand smoke exposure at initial concentrations. Which means it's more likely that there's a secondary curve. This is baseline lung function. There we go, we got it now. That's baseline lung function. This is the reduced lung function. This is the initial exposure. Initial exposure lung function. That p-value of less than 5% tells us there's almost no probability that, assuming lung function was actually unaffected, we got the lowered lung function. Look for the contradiction. Look for the contradiction. Here it is right here. We're assuming that secondhand smoke has no lowering effect on lung function from 0 to 1 hour. We make that assumption. That's why we tested against this curve, this blue curve. Well, the problem is we got data that doesn't agree with that. We got data that's so far off to the side that it's hard to believe it's on that curve. And it's easier to believe it's on that curve. Now, I don't exactly know where that curve is. This is Will's point from before. I don't know exactly where that curve is. But I just know that it is what? Say, Drew, say this aloud. That it's just lowered. That's all we can say. It's statistically significantly lowered. Jesse, it might be 0.1/10 of 1%. But it's statistically significant. The margins of error have shrunk down, and I'll touch it anymore. Fair? Be brave, people. You know this. Okay. Now here's a question. First question. Does secondhand smoke appear to affect lung function? What do you think? Based on this? Yes, negatively. Badly, right? It appears to affect it negatively. Could we be wrong?
Yes.
Good. How could we be wrong? How could we be wrong?
There's that 3-hour baseline.
Oh, forget that for a second. Eric, thank you for that. We're going to come back to that if you don't mind. I'm talking about right now from 0 to 1. Could we be wrong with our assumption? I'll give you a hint. Get that away. Why did I put that green curve there? Just out of curiosity. Now that I've erased it. Why did I put it there in the first place?
Because it doesn't really fit the second curve.
Good. It doesn't. Why doesn't it really fit the second curve again? Kaylee, go.
Because it's in the red part.
It's in the red part of that curve. But it doesn't really fit the blue curve because it's in the red part. But isn't it in the red part of the curve? So is it possible it actually is in that curve?
Yes.
Yes. Is it probable that it's in that curve? No, but it's possible but not probable. Okay, Kaylee, what's on your mind? What's on your mind right now?
Yeah, no, just I was thinking of the other one where the breast cancer green tea one, we had to add another curve because it is in the curve, but it's not probable it is actually.
Good, perfectly said. Perfectly said. It could be in either curve. It's more probable that it's in this one than this one. But that doesn't mean it can't be in this one. It just means that it's less likely in that one than this one. So, we could be wrong. And the question of how is that what did we get in our data? And what happens 1 in 20 times? What do you get? What kind of data? Starts with an O.
Outliers.
You get an outlier. You get an outlier data set. That does happen every once in a while. That does happen every once in a while. By this definition, it happens 1 in 20 times. Think about why. Think about why. Back to 243 now. Back to 243. Within 2 standard deviations of average, lie how much of your data? Within 2 standard deviations of average, lie how much of your data, percentage-wise? 95%, Danielle. 95%. That means outside of 2 standard deviations of data lies how much? 5%? 5% is 1 in 20. 5% is 1 in 20. That means out of 20 trials you run, one of them is going to be outside of, on average, and this is what your second project is all about, just so you know, FYI, the one to do like next week or the week after, I forget exactly when. 1 in 20 of those trials on average, you're going to miss big. And when I say big, you're going to miss outside of 2 standard deviations. And so something like this is going to happen, where you're going to get deviant data that appears to be somewhere else than it should be, but it actually does belong right here. And if you ran, say, hundreds of trials, you would see that that was one of the goofballs. The trick is, you don't know because you usually run 1 trial. So, what you assume is that it's not an outlier. You assume the 19 and 20 chance that it's not an outlier, but admit the fact that it might be. And this is why it's all gray, friends. It's gray. We'll come back to that momentarily. Let's go back to at 3 hours now. Okay, so right now we could have been wrong then, correct? We could have been wrong then. Just keep that in the back of your mind. We most likely weren't, but we could be wrong with that 5% chance. Come back to that. Okay, here we go. Then we're going to stop inundating our subjects with smoke after 1 hour. We're going to take them out of that room, take them out of the smoking room in Las Vegas or Salt Lake City, where that smoking room is. Put them outside, beautiful Central Oregon air. Essentially what I had to do for 3 days after playing punk shows at Players, just flush out the lungs. You ever do that when you try to squeeze every bit of air out of your lungs? Because usually when we breathe, we don't expand our lungs all the way. Try that sometime, it's phenomenal. Go out and clear air, like a clear morning, and just take a wicked deep breath and then exhale, and then keep exhaling. Do it until you can't do it anymore. It's amazing how much air is in your lungs that you don't really cycle. So we do that for 2 hours. And then we re-measure. So what I'm going to do is, if it's okay with you guys, to save some board space, I'm going to reform. Oh, let me swing back over here. Just for those playing the home game. We're checking the next set of p-values now, which are at baseline levels after 3 hours. Okay. So, to save board space and to keep that screen down so we can use it for comparison, what I'm going to do is, using a different color, we'll use orange, I guess. I'll put after 3 hours. Secondhand smoke has no negative effect on lung function parameters. And also, after 3 hours. Secondhand smoke has no negative effect on lung function parameters. So it's the same in words. It's exactly the same sentiment. It's just, when are we checking? Are we checking at initial exposure, or are we checking after hours 1 to 3 have passed and we've allowed the lungs to kind of flush smoke out? Good so far? Okay. Orange marker coming at you. Who wants to place the asterisk? On the curve. Remember, we're still testing against this curve. Because the assumption, as the null tells us, is always that secondhand smoke does nothing. Who wants to place the asterisk on this curve where it goes? You got this, that's great. The p-value tells you everything. What's the p-value tell you? That it is bigger than 5%. Jack, here we go. Camera's on, okay? You're the man. Go for it. Look what his hand is doing. Did you see what his hand is doing? He's going like this. He's going like this all over the blue region. Does he know exactly where it is in that blue region? No, but he knows where is it? It's in the blue region. It is in there somewhere. Because, well, first of all, by the words. At 3 hours, they were at baseline levels. Now, Jack, I love what you invented to do. You put it right in the dead center. I love that. Because on average, it's going to end up there if they're back at baseline. But then he put this little tiny range around it, which I love. That's fantastic, isn't it? It's fantastic. Because now he's given us that sway. Chances are they didn't come right back to here. They may have been even slightly lowered. But it's not anywhere near the statistical significance the lowering was from 0 to 1 hour. Thank you, Jack. That was perfect. Fair enough? You guys buy that logic? You buy that graphic? I want to talk about that graphic some more. That was perfect, Jack. Thank you, friend. Here is the conditional statement in words. We were expecting secondhand smoke to not lower lung function, and guess what we saw? Non-lowered lung function. So in other words, after 3 hours, we were expecting baseline levels, and what did we get? Baseline levels. Is that a contradiction? That's perfect agreement. That's the opposite of a contradiction. So the question, does it appear to affect, the secondhand smoke appear to affect lung function after 3 hours? No! It seems like the lungs have flushed everything out and filtered everything back, and we're back to baseline. Fair? Okay. Could we be wrong?
Yes.
Sorry, I'm getting louder as the day goes on. Could we be wrong?
Yes.
I can't do that. Yes, we could be wrong. Cassie, tell me how.
Well, it's a sample, so we could have done something wrong. Right?
So, exactly, it's a sample. So we could have, again, gotten outlier data. It's possible that the lung function is still completely down low, and we just happen to get one of those outlier data points. Back over to here. Okay. Is it possible, is it possible that our curve is still down here somewhere? Is it possible that our lung function curve at 3 hours, so here's the initial exposure lung function. I'm going to bring this down here. Here is the 3-hour lung function. Is it possible that we're down there?
Yeah.
Possible. Is it probable? No, it's not probable. It's not probable. The trick with this is I can't measure this directly. For example, remember when we were potentially wrong before? When we said lung function was reduced and we admitted the fact that we could be wrong. We said we could be wrong. Maybe lung function is actually not taking a nosedive and we got with a 1 in 20 shot. And we can actually identify the chance of that happening. Because the only way that's going to happen is if we ended up in that tail as an outlier. And that happens how often?
1 in 20.
1 in 20. 5%, 1 in 20. Perfect. This one's a little more nefarious. We could be wrong. But what's the chance of landing in that tail? Don't answer that question, because you can't. Because here's why. The only reason you can answer that question in the future is because you have to have some idea of where this is. And that's the kicker right now. If all you're saying is we could be wrong because lung function could be lowered and we missed it, well, if you're saying that lung function was lowered, that means you're also implying that it was lowered a certain distance. Hold that thought for like 4 or 5 weeks. In other words, forget it right now, come back to it. Let's be realistic, right? Fair enough? So, what we have just talked about, did you guys catch the difference between the last 2 studies? Let's look back up here again. I shouldn't say the last 2 studies, the last 2 parts of this study. The last 2 parts of this study, one of them showed that lung function was reduced, and one showed that it wasn't. I think, say that
There
again.
was a fine line between the studies, though.
When you say fine line, what do you mean, Cassie?
I mean, they were really close. Like, it's only 3 hours that you're testing people at 1 hour and then you're testing
I love
people at
this.
3 hours.
Jack was saying something similar earlier. I love this. I love this. The hope is that whoever does these studies knows that 3 hours, although it might seem like a tiny amount of time, is enough time to process whatever's going on in the body. That's the hope, huh? That's the hope. That's all I can say is it's hope. Can't say much more than that. Fair? Good. Okay, thank
You
you.
mean like physiologically?
Physiologically, yes. I'm hoping that these people that study this stuff have studied it enough to know that, okay, after 2 hours of pulling them out of exposure, any additional, it's diminishing returns at that point. Yeah, they're still flushing, because, I mean, I'm assuming it has a half-life like anything else. I could be wrong about this. But you've gotten rid of 99.999%, and any additional time, you're just keeping the subject around paying them more for no real gains. Is that fair? And that's why it's a great point that you bring up. Question the variable. Question the measurement. I mean, I'm putting lung function parameter in the middle of this curve and pretending like it's meaningful because I hope it is. Did you catch that part? When Chris asked the question about what a crossover study was, I went to the Wikipedia page. It pretty much is the same thing I was describing. But they said something about the lines of... I just lost that thought, damn it. Crap, I just lost that thought. I was tired. It'll come back to me. But the point is, question the measurement. Question the measurement, because if you change how you define the measurement, that might shift the curve over enough to create significance just by changing the definition. That's bogus, in my opinion. Okay, now, in this one, we said lung function was negatively impacted. In this one, we said it wasn't. Think back to 243. If you had me for 243, your very last project was about what? Do you remember? I'll give you a hint. Lyme disease, Down syndrome, HIV, spam emails. What were we talking about in that project? Lyme disease. Why would you care about Lyme disease?
Were we talking about probabilities of getting it?
Yes, we were, about not necessarily just getting it, but also getting it and...
Oh, actually contracting the
Well, contracting it, but once you contract it, you might not know that you have it, so you go and take a
Test.
boom! You take a test for it, which might come back false positive. Thank you, Ryan. Thank you, Cassie. So you take these tests, these HIV tests, these Lyme disease tests. I mentioned spam in there, which might have thrown you for a loop, but when you get a spam email into your inbox, your spam filter works like a disease test. It has to identify it based on all kinds of characteristics, whether it's spam or not. It could be wrong. How many of you have gotten spam in your inbox? Yeah? That means spam outsmarted your spam filter. I like to give them a little pat on the back before I delete them, because it's pretty amazing. They broke your spam filter and got through it. Hopefully, if you mark it, before you delete it, mark it as spam. Because that way it teaches your spam filter that much more how to identify spam. It's great mathematics behind that, actually, if you're interested. If you're not, that's totally fine too. But here's the deal. When you make a decision based on data, 4 things can happen. You can say that somebody has a disease and you can be right. You can say somebody has a disease and you can be wrong. Or you can say somebody, say it, be brave, doesn't have the disease and you can be right. Or you can say somebody doesn't have the disease and you can be wrong. 4 things can happen. 2 of those are falses, as Ryan pointed out, and as Cassie pointed out, 2 of them are correct. When you say lung function was reduced, that is a positive test result. Because you are assuming the opposite. But you got data that tipped the scales, and you say, it's a positive test result. As soon as you say as soon as you think of it like a positive test result, you realize there are 2 possibilities. True or false positive. Hold that thought. When you say that lung function did not change from baseline after 3 hours, that's a negative test result. Because you say nothing's changed. You could be wrong with a false negative. So there are 2 ways to be right, 2 ways to be wrong. I want to analyze the ways to be wrong right now. Because this is as important as being right, minimizing the ways to be wrong, if that makes sense. We'll come back to that. Okay, here we go. Ways to be wrong. You get a small p-value. As a researcher, how do you feel? As a researcher, how do you feel if you get a small p-value? Happy. Why do you feel happy? Well, go. I agree with you. Or happy because?
Your study's showing something meaningful.
Your study is showing something meaningful. When you set your hypotheses up, you get a small p-value. Who do you believe? H0 or H1? Do you believe the null or do you believe the research when you get a small p-value? Let's swing back over to there.
Research.
Yep, you sure do. Let's drive this point in your brains right now. This will make the next 8 weeks easier. 7 weeks easier. When you get, oh please Kaylee.
No, I just have a, will you quickly define p-value again for me?
Sure, I'm going to have your classmates do it because they won't talk today. I have 20 more minutes to make you say something. So, small p-value supports this. But Kaylee brings up a very good point. Why? Why does a small p-value support the research hypothesis? Who wants to tackle that one? Make me call names. Start calling names.
Help.
Help! Help! We need to hear this. What is a p-value? What does the p stand for? Capital P. Cassie said this word about 2 minutes ago.
Probability.
It's a probability, Dina. Thank you. It's a probability. Let's answer Kelly's question in pieces. It's a probability. What is it the probability of? Let me give you some examples so then you can answer. I'm going to flip back through your slides and show you a bunch of the ones that have been written down. Remember what kind of probability it is? Starts with a C. Ends with unditional. That's right. Here's one right there. Check out what it says. It's a probability. We got non-lowered lung function data given secondhand smoke doesn't lower lung function. There's one of them. Notice that's a big p-value. Big B, bigger than 5%. Back up again. Here's another one. Probability. We got lowered lung function data given secondhand smoke doesn't lower. Notice that p-value, big or small? And why is it small? Because what happened here? Say that again, Danielle. It's below 5%. That's why I put small in parentheses or in quotes up here. Small means less than 5%. What about these two pieces of the probability? What do they do to each other when it's small? I heard it stereo. They contradict each other. Perfect. They contradict each other. So let's back up again. Let's go back to green tea, maybe. Here we go, green tea. Here it is. We got lowered breast cancer rate data, assuming we weren't going to. What's that right there again?
Contradiction.
That's another contradiction. How do you tell it's going to be a contradiction without even reading the words? What tells you it's going to be a contradiction? Eric picked this out immediately last time.
Less than 5%.
0.001, 1 to 1,000. Here we go, let's back up some more. This is the worst answer ever, right, Kaylee? Yeah. I can't just tell you the answer. No, I gotta drag it out of you. Here we go, here we go. Back, 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 back. Oh, I think it's on this page. No, maybe it is. Here it is. We got lowered heart rate data, assuming caffeine's not going to lower heart rate. Contradiction or not contradiction? Is that a contradiction?
Yeah.
Hell yeah, it is, because you said caffeine wasn't going to lower heart rate. But what did it do? It lowered heart rate. How can you tell it's going to be a contradiction? Where's the indicator?
Less than 0.05.
Exactly, the p-value less than 0.05. Now, here's ones where there aren't a contradiction. We were expecting caffeine not to lower heart rate at rest, and guess what? It didn't lower heart rate at rest. Look at the p-value, bigger than 5%. We were expecting caffeine not to lower heart rate during max exercise, and guess what? It didn't lower heart rate during max exercise. Bigger than 5%. So, let's answer Kaylee's question. When we get a contradiction, the p-value comes back big or small? Be brave!
Small.
Small!
Wait, say that one more time?
When we get a contradiction, don't memorize this part.
Right.
When we get a contradiction, the p-value comes back small to indicate a contradiction. Why is the contradiction what the researcher is looking for? This is the key part. Why does the researcher want a contradiction?
Your study shows something meaningful.
Danielle, say that again.
The study shows something meaningful.
Whatever variable you're measuring deviates from what is expected. What is expected is the status quo. What has always been there. Caffeine raises your heart rate. Green tea does nothing for breast cancer. Secondhand smoke does nothing for lung function. Blah, 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 blah. Right? So caffeine does nothing on heart rate. Green tea does nothing for breast cancer. Secondhand smoke does nothing on lung function. Then we test it. When we get small p-values, we realize, oh my God, caffeine does do something on heart rate. Oh my God, green tea does do something for breast cancer. Oh my God, secondhand smoke does do something for lung function.
And that indicates a small p-value.
Yes, ma'am. When we're expecting nothing to happen and something happens,
Okay.
that's a small p-value, that's a contradiction. You got it.
And both of those are more than
Which means contradiction or no contradiction?
no contradiction.
No contradiction, because we were expecting caffeine to do nothing and caffeine did nothing. You got it, my friend. So if you look at each of those conditionals throughout this entire set of slides, every single one of them, any one where the right-hand part, which is the null assumption, agrees with the first part, which is your data, you get a big p-value, which means the researcher goes, well, it's worth a shot. I can't publish this anymore. It's worth a shot, right? The small p-values are the ones you're going to read about in research papers because they're the ones that showed something changing in some way. Fair? Kaylee, does that make sense?
Yep.
That was the longest answer ever to your question. I apologize for the length, but it's important.
Well, it was more basic. It was kind of going backwards, but I just kind of wanted to
Good for you.
cap on the beginning of yesterday to make it all come together.
If you guys understand nothing at the end of this class than what a p-value means, I'm stoked. I hope you understand a lot more. But if that's the only thing you take away from this class, and this was hilarious because that was one of the 5 things on this guy's first slide. Know what a p-value is and its interpretation. I'm like, oh, thank God, somebody else thinks like me, which is a dangerous idea in and of itself. Fair enough, Kaylee?
Yep.
Fair enough, everybody? Who's got questions on that? Right, I'm going to get caught back up here. Sorry, YouTube world. Going kind of quickly. Okay, here we go. So, we get a small p-value. Automatically, when you get a small p-value, you believe the research hypothesis. And you say, man, it looks like the research hypothesis has some merit. What that is called is reject. This is formal now, just so you know. This is formal. When you get a small p-value, The formal language is you reject the null hypothesis. Just so you know, you'll hear that phrase from time to time. You reject the null hypothesis. Being a glass is half full kind of guy, I like to support the research hypothesis. It's kind of how I say it. And I don't like you guys using the word reject and fail to reject in this class, so I will tell you to write this stuff out in words. That's what I'm after. I like communication of statistics rather than just formality. So, here's the response. Something changed. I was expecting caffeine to do nothing. Caffeine did something. I was expecting this. That happened instead. So, could we be wrong?
Yes.
Of course we could. What's the chance? You have to know the answer to this. You got it drew nice and loud. 5% chance. Why is it a 5% chance, friends? It's almost a silly, it's a silly simplistic question. I think we may have answered it with Kaylee's question. But why is it a 5% chance that we're wrong? And why could it not be, say, a 0.001 or a 0.003 or something like that chance? Give you a hint. Confidence. Confidence.
Because we're 95%.
Because we're operating on a cutoff of 95% confidence. Anything that falls outside of 95% confidence is going to make us go, whoa, something changed. So it's by definition why it's 5%. It has to be 5% because we've made it be 5%. If you test at 99% confidence, it's going to be 1%. If you test at 98% confidence, it's going to be 2%. Let me just give you a think of what the free advice as far as good statistics, bad statistics. If you're out there doing research, and you do a research study and you get a p-value of 6%, don't change your confidence to 90% so that 6% becomes significant. I find out you do that, I come kick your butt. Statistically, of course, give you a firm talking to. We have ways of dealing with 6% p-values. We'll deal with them in this class. If you think something is actually going on, don't fake your data. There's ways to do it soundly. We'll come back to that. But just don't let me catch you doing that. So here's the deal. Here's the deal. That would be, can you see why that's called a false positive? False positive, that means you said something changed. That's a positive test result. You got Lyme disease, something changed. You don't go in assuming you have Lyme disease. You go in assuming you don't, and the test comes back positive, you go, oh, crap. But you only go, oh crap, if the test is right 100% of the time, which they never are. There's always a chance you can be wrong. With a statistical test, by construct, it's usually 5%, which is that same symbol alpha I mentioned before. That's the same symbol. We set that up because we're setting up a 95% true negative confidence interval. That has to have a 5% false positive tail. We'll come back to why the other part is true negative next time. That's a little much to deal with in one day. The 95% part of the curve would be the true negative curve. The 5% tail is the false positive. And some of you might be saying, why the hell wouldn't that be false positive, true positive? We'll come back to that, I promise. That might make a lot of sense today. It's called a type 1 error. This is historically what they're called, is type 1 errors. I like to call them false positives, but because I'm training you guys potentially for more statistics classes, we'll go with both, the type 1 error. I'll mention it both ways in class. That's how you can, that's one way to be wrong. False positive. With me so far? That's good. So, here is from the article, secondhand smoke article. 0 to 1 hour, most lung function parameters were significantly reduced. So in other words, we said lung function parameters were significantly reduced. Could we be wrong? Yes. Finish the statement. We could be wrong by saying lung function parameters were significantly reduced, comma, when, in fact, comma, they were not. Simple. We could be wrong because we said they were reduced and they might not be. That's what I call defining error in context. We could say lung function parameters were reduced when in fact they were not. Looking back to our curves, you can identify where that is, can't you? You can see where that is on our curves, can't you, friends? It's going to be right about there. Somewhere in here. You can't see that except on the camera. It looks really great. Somewhere over here. Who is this? Eric? This is Eric. Your placement was perfect. If we land somewhere in here, we believe this guy. We believe the research hypothesis. It looks like we're too far away from the center of the curve. How could we be on that other curve? Well, it's not likely, but it's possible. And that's the type 1 error, possibility. Fair-ish. Good, maybe. Getting there. Okay, type 1 errors are simple. Type 1 error is 5% likely all the time as long as you test at 95% confidence. No question, no problem. Danielle, go please.
So are you saying type 1 errors are the false positives?
Yes, ma'am, I am. They are always, they're considered false positives. I like that phrase better because type 1 error doesn't have any kind of context, but a false positive is you said something changed, but it didn't. False positive. So, and it's always going to be 5%, assuming we're testing at 95% confidence, which I do every time in this class. Sometimes your textbook mixes up a little bit, but I always test it at 5% significance or 95% confidence. Thank you, Danielle. Great question. Let's swing this back. Let's look at other ways to be wrong. Okay. We'll stretch this into Thursday after your exam. We'll finish this up on Thursday after your exam. You know what? Yeah, let's go a couple more slides, and then we'll call it. We'll finish this after your exam. Okay, now that's if you get a small p-value. That's if you get a small one. What if you get a big one? So you get a big p-value. What's big defined as again, friends? Big is defined as above 5%. I don't care if it's 6, I don't care if it's 60, I don't care if it's 6.2, which it can't be, but whatever it is, it's above 5%. Okay. That's your common response. Nothing changed. Which hypothesis do you believe? Say it nice and loud. Somebody just said it. The null. Yes, you believe H naught, the null. Nothing changed. You go into the study assuming the null. You get data back that says, yeah, the null looks correct. Just so you know, the common phrase for this is failing to reject the null hypothesis. That's just the common lingo. It's antiquated is what it is. It's antiquated. Because I remember studying statistics back in the day, and that's all our prof wanted us to say. Do you reject the null, or do you fail to reject the null? I remember going through that course not knowing what the hell I was doing, but I could circle the right answer all day long. Go, Kaylee.
And this is bad for researchers or scientists because they're not finding anything significant.
Right. Assuming they're looking for a change, a researcher doesn't want to see this because a change would be a small p-value. Thank you, my friend. So if you get a big p-value, a big P supports this guy. Get big P support the null. So what I would say, instead of, I'll keep saying in class from time to time, fail to reject the null, because in case you guys have other stat classes, I don't want you to walk in there thinking I never used that terminology. But most of you aren't going to take one. How many of you are done with the stat class? Yeah, I want you to read research. How many of you are not, that you know you're not done? How many of you know you're not done stat? Jad, you got more stat, Laura, you might?
Is there any like biological statistics?
Not here, maybe at OSU.
Okay.
Potentially.
Yeah,
But see, that makes me all the more happy about not using the formal language all the time. Here's what I would do. So for example, we get a big p-value like we did at 3 hours in the secondhand smoke article. What makes more sense to your neighbor? Imagine you're out pulling weeds in your garden. Talking to your neighbor. Yo, I read that article about secondhand smoke. After 3 hours, you've got to fail to reject the null hypothesis. Or, it looks like after you have somebody exposed to secondhand smoke for an hour, and then you pull them out for 2 more, it looks like their lungs are back to normal. Which one of those 2 statements makes the most sense? The second one, which is what I have you guys writing in this class, conversational English, rather than rejecting and fail to rejecting. We'll find you some biostats, I promise, Laura. We'll find you at OSU. I'm sure they exist.
Awesome.
Yeah, what you need is you need a statistics department, which we don't have at a community college. Don't have those. We're not big enough to have stat departments. I wish we were. Right? There's 2 of us in it, me and Donna. Anyway, what's the chance that you're wrong? Chew on that thought for next time. We're going to pull the plug here on it. Because I'm not going to finish this in 5 minutes. I don't want to finish this in 5 minutes. So what we'll do next time, we'll start with the exam. We'll wrap this up and probably do our first hypothesis tests after your exam too. It'll get some fun. Actually crunch the numbers ourselves. State hypotheses. Have some fun. All right, friends? All right, we'll catch you next time. Study hard. Email me if you get stuck with anything. Kelly, what you got?
I got some questions.
Well,